Okay, let me start with a brief summary of what I'm going to talk about in this lecture. In structural microeconometrics, a very important concept is the concept of reveal preference. We observe agent choices. We assume that these agents are maximizing, optimizing a criterion function, profit, utility, anything else. And then this simple idea implies that their choices reveal information about the structure of the payoff function that they are maximizing, about how this payoff function depends on actions and state variables. This is a very powerful concept in economics or in econometrics, if you want. If we are in the context of decisions under uncertainty, the reveal preference concept is going to reveal information about the expected payoffs of the agents. Expected payoffs are a combination of the structural payoffs and the distribution of the variable that the agent is uncertain about, okay? Then for most empirical questions in economics, in particular counterfactual questions, we need to disentangle these two components, the profit function and the distribution of the variables that the individuals do not know. That is the payoff function and the beliefs, let me put it that way, okay? The most standard approach in econometrics, despite all the papers that we have seen in this conference and the recent emphasis or interest in using elicited beliefs, the truth is that it's still rare to have elicited data on subjective beliefs. And then the most standard approach is to assume rational expectations. The distribution of the beliefs corresponded to the true distribution of the variable. And then we can estimate in many applications the distribution of the uncertain variables. And then we, taking into account that using reveal preference, we can identify expected payoffs. Given expected payoffs and the distribution of uncertainty, we can now identify the payoff function, okay? This lecture today deals with some results, some identification results, where we can relax that assumption, okay? We can relax the assumption of rational expectations or rational beliefs. And the idea is we can interpret it, or let's consider again, using reveal preference, we can identify expected payoffs, okay? Then the identification problem is not the identification of expected payoffs that is given by reveal preference. How we disentangle from expected payoffs the payoff function from the beliefs, okay? That's the key identification problem that I'm going to talk about today, okay? And what I'm going to show is that particularly I'm going to focus in games of oligopoly competition, either static or dynamic. There is a type of exclusion restriction that I'm going to argue that is plausible in many applications in industrial organization, in models of oligopoly competition. There is a type of exclusion restriction that can give us separate identification of payoff function and beliefs, okay? And then, using information of belief, of course, we can test whether there are rational beliefs or whether they correspond to some particular equilibrium concept. We have having to impose that equilibrium concept for the estimation of the payoff function, okay? Okay, then I will start with a little bit more of context of this problem. I will start with static gains because everything is simpler in that case, the model and the identification result. I will move then to dynamic gains, and if I have time, I will talk about a paper with Arvin Magnuson, when we applied this identification argument. Okay. Okay, then we know that in oligopoly markets, firms have to make a decision. They have to form expectations or beliefs about how the competitors will behave. Agents can have different information or different ability to process information and to gather information. And this can generate heterogeneous beliefs of these agents. Okay? Reasons for these heterogeneous beliefs: limited information, limited attention, some form of bounded rationality, like Ariel has mentioned before, computing the correct best response can be super complicated in some strategic contexts. And also in the context of games, something that has received a lot of attention from experimental economists is a strategic uncertainty. Imagine that we are typically many models of oligopoly competition, either static or dynamic. We can have multiplicity of equilibrium. Okay? And suppose that we are considering a pricing game in a differentiated product market. There is a strategic complementarity in this pricing game. Then we can have multiple equilibria. We can have an equilibrium with relatively low prices, other equilibrium with high prices. Okay? Suppose that there is a merger. Okay? And then after the merger, suppose that in the initial equilibrium before the merger, first they have been playing for a while, and everybody knew that they were playing the Bertrand equilibrium with low prices. Okay? Then after the merger, now there is a strategic uncertainty. There is a new equilibrium. Okay? And firms may have some doubt about, will we continue playing the low price equilibrium? Or given that now there has been a merger, it might be that we are going to move to the equilibrium with high prices, to the new Bertrand equilibrium with high prices. Okay? And then for a while, at least for a while, we might have that some firms believe that they will continue in the equilibrium with low prices, in the new equilibrium, but with the low price type of equilibrium, or other firms will believe that we are going to move to the equilibrium with high prices. Okay? And then everybody is rational here, but there is no coordination in the type of equilibrium. And then they will end up, nobody will have correct beliefs. Okay? Because they are playing different games, different equilibrium. Okay? Then, sure.
Start from the same prior or
They start from the
same prior. Do we have a common prior or not necessarily?
I'm not taking any stand on that. Okay, it's just for a while they will not know what is the new equilibrium that they are going to play, that they are playing. Okay, and there will be. This could last eventually forever, depending. And I think that Xavier Vives have papers. Have several papers about convergence to an equilibrium or not, and then there are conditions with some particular learning conditions and some particular conditions on the prior. These firms will converge to the same equilibrium. In other cases, they may not. Okay, thank you. Please.
Sunspots shocks the leaves and that. Like leads to indeterminacy of the
It's not strategic uncertainty is not so much related to sunspot. I think at least my interpretation of sunspot will be more related to different equilibrium in different markets. Okay, that we observe. Suppose that in this industry there are multiple local markets. Okay, in different regions. And we have that two markets have exactly the same fundamentals, the same competitors, the same cost, the same demand, everything the same. But in one market we have one equilibrium, and the other market we have other equilibrium. Why? Because they have these selected different equilibria. And why they selected different equilibria? A sunspot. Okay? Okay. Here I'm talking more about the same market, okay? There is no role for a sunspot. It's just something happened and they don't know, okay? They don't know with sunspot, people are playing an equilibrium, okay, but different in different markets with the same fundamentals. Here, no, we have that nobody's playing an equilibrium, though everybody's best responding to an equilibrium, but they are best responding to different type of equilibrium. Okay, please. Oh, that's a great question. Okay, that's a great question. I have been searching for that for a while. Yeah. Yeah, it will be great to have empirical papers. Of course, there is a lot of empirical evidence in the lab. Okay. But in terms of data that tell us really, there are several papers that claim this, but I haven't found really any paper with clearly convincing evidence that this cannot be explained because difference in fundamentals. This is really a strategic uncertainty. Okay, that's challenging. I think that conceptually makes sense, and I think that it should have happened somewhere, but I don't know of any papers that have shown this in a convincing way. And it's an interesting question, challenging but interesting question for research. Yeah. Okay, let me skip this. There are several empirical applications showing evidence, especially in IO, showing evidence of biased beliefs, not necessarily giving a clear interpretation of what is the source of biased beliefs, but giving evidence of firms having biased beliefs for a while. What are the typical contexts where we should expect that this may happen? Well, young industries where firms do not know very well how their competitors will respond. They don't know very well the fundamentals of other firms or the cost of other firms. After the structural changes, we should expect that if there has been an important merger or some very important change in regulation, it can take a while for firms to learn about which equilibrium is playing. Firm heterogeneity in demand and in cost, it can be very difficult to know exactly what are the strategies of each of your competitors. Okay, you can have an idea or you can learn relatively quickly about the average response of your competitor, but to have the correct strategy function, you may need to know exactly what is the strategy of each of your competitors. Okay. And there are different scenarios that they can make this more likely. Okay. Then let me start with the static games. Okay. And then we have n firms competing in a market, and each firm has this type of profit function. We use I to index firms. A is the action of firm I. Bold A minus I is the action of the other firms. And then we have two types of state variables or exogenous variables affecting the profit. X, that is common knowledge to all the firms, and epsilon, that is private information. Okay? Soon, I will assume that these epsilon are independent private values, but for the moment, they have a joint probability distribution F. Okay? Then I'm going to consider both in the static and in the dynamic framework, I'm going to consider games of incomplete information, where we always have these epsilons, okay? Where firms do not know everything about the competitor, okay? Then the game consists that these firms choose simultaneously their actions A. For the moment, A can be continuous, discrete, single value, or multivariate, okay, it can be anything. Okay, and for a while, I will try to be general in that respect. Okay. These are the payoff functions. To make an optimal choice, a firm needs to have some beliefs about what will be. Then, the moment the firm I wants to maximize this profit function, okay, but he doesn't know the actions of the other firms because the actions of the other firms will depend on the epsilons of the other firms. And this firm doesn't know the epsilons of the other firm. Then it has to form some beliefs, or what this firm can maximize is his expected profit. That is, this profit function integrated over the distribution of the actions of the other players. Okay? But to maximize this expected function, or to construct this expected function, expected profit function, it needs some distribution of the actions of the competitors. Okay? Then, for the moment, because we want to be general about this model in terms of both payoffs and beliefs, let's consider a very general function of beliefs. This is a distribution of the action of the competitors that is firm-specific. Two different firms can have different beliefs about the behavior of the same per firm in the market. And of course, as Ariel has mentioned before, and is of course obvious, either actions or beliefs of someone may depend only on the information that this person or this firm has, okay? And in this case, this information is the common knowledge variables and the private information variable, okay? Then given these two elements, the profit function and the beliefs, this is the expected profit of a firm, okay? Just the integral of the payoff over the distribution of beliefs. And then, given we assume that everybody is maximizing expected profit, this is the reveal preference assumption, okay? We assume that everybody maximizes this object, okay? Then we have an optimal strategy function that depends on the information that the firm has, these payoff relevant variables, and depends on the beliefs, okay? Very simple. It's convenient to represent optimal behavior in terms of marginal conditions of optimality, okay? Then we are going to represent the best response of these firms in terms of first order conditions of optimality, where these first order conditions can be continuous or discrete, okay? And then I'm going to use a common notation that includes as a particular case when we have a continuous action, then delta pi, if we have a continuous action, is just the derivative, the partial derivative. And if we have a discrete action, this delta I is just, for instance, the profit between the difference between the profit of having two firms versus one firm, or the difference between having a high price or a low price, or the profit of being in the market and not being in the market, okay? Then these games with incomplete information can become very complicated, something that facilitates very much the definition of an equilibrium and operating empirically with an equilibrium is what is called a single crossing condition in terms of the private information, okay? Then to have this single crossing condition, we assume that this marginal profit, either continuous or discrete, is such that it has a component that depends on the actions of all the players and the common knowledge variable, plus or minus the additive, the private information in an additive way, okay? Then this is going to facilitate very much our life, okay? Introducing the private information additively in the marginal profit, okay? And then we make other additional assumptions that facilitate also the empirical analysis and the computation of an equilibrium, okay? Independent private values, private information is independent across players. The CDF of the private information, that is the same for all the players, is strictly increasing, no mass of probabilities. We have continuous variable over the whole Euclidean space. And condition C that we can see really as an implication of condition R. If the private information is independent across players, and we have players that are a little bit sophisticated, then they realize that the information that they have about their own private information does not contain any information about the actions of other players, okay? Therefore, their own epsilon does not play any role in the predictions of the actions of the other players, okay? And you can see this as an assumption because you could say, okay, but they could not be sophisticated enough and they can use their epsilon to predict. Then in that case, we are making the assumption that beliefs do not depend on the private information, only on the common knowledge variable. Okay? Okay, then now what we have is that the expected marginal profit, it can be represented in terms of the expected marginal profit that only depends on the actions of the players and the common knowledge variables. Okay. And then a necessary and sufficient condition for the optimality for the best response for choosing action A. Okay. In the continuous case is that this marginal profit condition holds, okay? Epsilon is equal to this marginal profit that does not depend on epsilon. And in this discrete action space, we have basically two inequalities in terms of the private information. Epsilon should lie between the marginal profit if you have two stores in the market or if you have one store in the market, okay? That means that the optimal number of stores will be 1 if this condition holds, okay? Sure?
So suppose there were a state of the world, the combination of that state of the world is epsilon were correlated because the dependence of what would you accommodate?
Everything becomes more complicated when you have common values or affiliated values or some kind of correlated values. All what I'm going to present today is with independent private values, and I must admit that I have thought only on that case. I think that the identification results is not that there is any obvious impossibility result, but I think that that the results are going to become more complicated. Yeah. Thank you. Yep.
So I think for the continuous action, this is a first order condition, right?
This is a first order condition. And this is also, I'm called this also a marginal condition of optimality, even though they are discrete choice and inequalities. They are marginal at the extensive margin or marginal at the intensive margin.
So I understand why it's accurate, but why it's different?
Okay, you are completely right. Okay, we need some. Yeah, definitely, it's an implicit assumption here. Thank you. Yeah, I should add here another assumption that is concavity with respect to A. Yeah, thank you. Please. Yeah, these are independent private values, exactly. This is information, this epsilon is information of firm I and completely unknown by the other firms in the market.
Should we just think of them as like, say, the marginal costs?
Yeah, it depends on the particular application. In the case of auctions, is with independent private values is your valuation. In the case of Cournot competition over Trump competition, it can be naturally the marginal cost, a component of the marginal cost. In the case of models of at the extensive margin of market entry, this will be a component of the entry cost of the firm. Okay, thank you.
Uniqueness here.
Uniqueness of the equilibrium, not at all. Not unfortunate. Yeah, no. You can have multiple equilibria. The number of equilibria typically will be based on the work of Deraselsky and Escobar. It's possible to show that there is a finite number of regular equilibria, but in general, there will be multiple equilibria, unless we make some strong assumptions of homogeneity of these pi functions, yeah. Strong homogeneity and strategic substitutability assumption, because even with homogeneity and strategic complementarity, you can have multiplicity of equilibria. Yeah. Okay, then let me represent these conditions, okay, in terms of the distribution function of the actions, okay? Let me define this function P as the CDF of the actions of a player, okay, in a particular point. Then these marginal conditions of optimality can be represented in terms of the distribution of the action of player I conditional on X should be equals to the CDF of epsilon evaluated at the marginal profit at this action of player I, okay? And then let me define this quantile function that is just the inverse, okay, of the CDF of epsilon evaluated at this CDF, okay? And then basically we can represent the best response of a player using this quantile function. If we can estimate from an empirical point of view, if we can estimate these choice probabilities and we are willing to assume that we know the distribution of epsilon, basically this is the reveal preference approach, okay? Given that we observe the actions of the players, and in this case we know the distribution of epsilon, then we know this quantile function at every action and every possible value of the state, and this directly reveals what is the expected marginal profit, okay? The action of the player under the assumption that players are maximizing some function, they give us the marginal profits of the player. That's not, under the assumption that I have presented, that's not the identification problem. The identification problem is now how, given that this expected profit function is the convolution of the structural or primitive marginal profits and the beliefs, okay, how can we disentangle these two components from what we can identify from reveal preference? This is the identification problem that this lecture is about, okay? We want to disentangle these two components. Basically, at this moment, in a non-parametric way, okay? This is going to be a general marginal, general functions of the actions of the players and the observable common knowledge state variables. And at this moment, we don't want to claim that we have been able to separate beliefs and payoffs, okay? Because we assume that this is any particular parametric function, okay? It's important to be non-parametric here because we want to be able to claim basically that our separate identification of payoff and beliefs is not based on basically saying this is linear, this is quadratic, and I claim victory, no, of identification of this, no. Okay, these are, I will not go through the different examples, but you have here different examples. Cournot competition with here, you can see that the private information is in the marginal cost of the firm. And then we have a particular expression for this. This is an example of market entry with private information in the entry cost. This is the private information in the entry cost. This is a very common case of procurement auction with private information also in the marginal cost of the firm. Okay. Okay, then basically the restrictions of this model on the data are given by this equation. We have a probability distribution of the actions of a player, of a firm, okay? Condition on what, let me say that let's assume that we as researchers know what every firm in the market knows. We know X, but we do not know the private information of the firms. Then this is an object that we can estimate from the data. And then the problem is how to identify these two functions from this data, okay? At this level of generality, B can be anything, okay? Of course, different models and different empirical applications can impose different restrictions on these belief functions. The most common restriction in games of static games of incomplete information is the Bayesian-Nash equilibrium, okay? And basically, the Bayesian-Nash equilibrium says that everybody, the belief that firm I has about the behavior of his competitors corresponds exactly to is self-fulfilling, corresponds to the probability distribution of the actions of the competitors that comes from the best responses of the competitors, okay? And at the end, beliefs are in equilibrium, okay? And this equilibrium concept has been used. This is very common, especially in auction games, but also in discrete choice games of market entry, like Katja Saim's paper on entry competition, her paper in 2006 in the video stores. Okay. You have other assumptions not so common, but common in experimental economics, and there are some papers like Goldfarb and Xiao, where they consider cognitive hierarchy models and level K models they are equilibrium concepts, but equilibrium concepts, beliefs are in equilibrium, but they are beliefs in equilibrium which do not correspond to the actual probability distribution of the state variables. And everybody has biased beliefs, but there is an equilibrium where everybody has bias beliefs, okay? And you have also more general type of concepts or solution concepts like rationalizability, is that everybody knows that everybody knows that everybody knows that they are rational, okay? And that if there is a single equilibrium in the model, rationalizability will reduce to the unique Bayesian Nash equilibrium. But if there are multiple equilibrium in the model, rationalizability includes not only the different equilibria, but the example, for instance, that I described before. You believe that we are playing equilibrium A. I believe that we are playing equilibrium B, and we are both best responses to different equilibria, Bayesian Nash equilibria that the model has. Okay. Okay, then let's go to identification. And before we talk about identification, of course, we need to be specific about the type of data that we have. Okay. Then we have typically multiple local markets, indexed by M, and we observe the actions and these X variables for every firm, each of these N firms, in every market M, and in some cases over several periods of time. Here, because it's a static game, we don't need the time variation, but let me just include here the time variation. Then let me discuss the identification. Remember, we want to separate basically payoffs from beliefs in a non-parametric way, okay? Then let me start with the best ideal and very unrealistic scenario where we have choice data, that is, we observe the actions of the players, but in addition, the researcher has been able to estimate the revenue function before estimating this game, and suppose that the researcher is so lucky that has also data on marginal costs, okay? And let's see that case, and then we will consider more realistic cases where the researcher only has the revenue function, and finally, with only choice data and no information on the revenue or the cost function, okay? Okay, then let's distinguish between revenues and costs in the profit function, and therefore the marginal profit function is the difference between the marginal revenue and the marginal cost. Okay. Let me focus. Later, I will tell you that this result can be extended trivially to multiple choices. But let me focus on the simpler version of this game. Just a binary choice game. You can consider a model of market entry. Let me, instead of a model of market entry, consider a model of price competition where firms compete in charging either a high price or a low price, okay? Then A equals to 1 is the high price, A equals to 0 is the low price. And we have supermarkets competing in high-low pricing, okay? Then this is the marginal revenue, is the difference between the revenue with the high price minus the low price. The marginal cost, the difference in cost between the high price and the low price. And this is the data, basically for a firm I, and given the observable exogenous variable, what is the probability of choosing the high price? And this is the belief, this is observable from the data, P. This is the belief that firm I has about the probability that the other firm will choose the high price, okay? Then in this context, the expected marginal profit of firm I is the difference in his profit if he chooses high price minus low price, but integrated over the possible actions of the competitor, okay? And in this first term, we have what is the probability that he believes that the competitor will choose the low price times the marginal profit, okay? If he chooses the low price, if the competitor chooses the low price. And here we have the belief that the competitor will choose the high price times the marginal profit if the competitor chooses the low price. We can put together this marginal profit under 0, and then we can group all the terms where we have the beliefs to have this expression, okay? Then the probability, as you know, that the probability that given this marginal profit, the probability of choosing the high price is that the probability that epsilon is lower than this amount. And therefore, we have that the best response probability of the player is this expression, okay? Where this is the distribution of epsilon. We invert this distribution, and we have that this quantile function is equal to this expression, okay? And now, basically, in this expression, everything is observable except the beliefs. We know as researchers this quantile function. We know the marginal revenue. We know the marginal cost. What we do not know is this probability. But here, the reveal preference approach reveals beliefs, okay? Because basically, we know preferences, okay? Then we can just simply invert these beliefs from the data. And we have this expression for every possible value. And once we have estimated this from the data, now we can test equilibrium beliefs, okay? We have estimated these beliefs from this data, but of course we have also the probability distribution that the competitor charges the high price. This comes from all this reveal preference is not using at all the behavior of the competitor. It comes from the behavior of player I, okay? The behavior of player I reveals information about his beliefs on the behavior of the competitor. And now we can look at the actual behavior of the competitor and estimate this choice probability. And then the test of equilibrium belief will be a test of this restriction, okay? We can test. This will be a test of Bayesian Nash equilibrium. We can also test other type of restrictions on beliefs like level K or cognitive hierarchy or rationalizability, okay, or anything. Once, given that you have the payoff function, you can identify the rationalizable set of outcomes, and you can test whether these beliefs lies within the rationalizable test, okay? Or you can test specifically, if you know the different Bayesian Nash equilibrium of the model, if these beliefs corresponds to the case that we were discussing below. Player 1 believes that we are playing equilibrium A, player 2 believes that we are playing equilibrium 2, okay? Then once you have identified beliefs, we can test for different possible type of outcomes that may be consistent with these beliefs, okay? Now, this is very unrealistic, unfortunately, that we as researchers observe perfectly revenue, marginal revenue, and marginal cost. And let's consider a more realistic setting where the researcher observes the marginal revenues, but not the marginal cost, okay? Then we have the same expression as before, but now we have 3 unknowns. We have the marginal cost if the player does not chooses action 0, the low price, we don't know it, we don't know the beliefs, and we don't know also the marginal cost if the if the player chooses the high price. And without further assumption, we don't have any information at all about these guys. There is no way to rationalize this. Then give me any assumption about beliefs. This is common. This is the common problem for those of you who have studied IO before. This is the common problem to identify collusion, for instance. Okay. Give me beliefs that are consistent with collusion. Okay, and if I don't have any information about cost, I will be able always to find the cost function, or give me beliefs that are consistent with competition, no collusion at all, and I will be able to always to find costs that rationalize that these beliefs are correct, that players are behaving best responding to not colluding, but best responding to some competitive equilibrium, okay, or oligopoly competitive equilibrium, okay. Okay, then we can always rationalize, we can always find values of this marginal cost that given the observed behavior of the firms, can rationalize basically any beliefs. Okay? Okay. Okay. Then we are finally in the identification problem that we want to study. Okay? Then what is the type of exclusion restriction? Then one way of solving this is by having exclusion restrictions. Okay, there is something that enters in particular we are considering that something that enters in the beliefs, okay, but does not enter in the marginal cost. Or more specifically, in beliefs we will have everything. Okay, firms, we are not willing, again, we don't want to claim that we are identifying beliefs and payoffs separately because we are imposing restrictions on beliefs. We want to be very non-parametric and general about the specification of beliefs. We don't want to touch this object at all, okay? But there may be economic restrictions that are reasonable, that tell us that some variables that are in X, that some variables in X do not enter in the marginal cost of a firm, okay? Let me try to argue that we can have this type of exclusion restriction, okay? Then let me consider that X, okay? X will include variables that affect the demand of these firms and the cost of these firms, okay? The marginal revenue and the marginal cost, okay? Then suppose that we can separate this X in three components, okay? The variables that are common to all the firms, and then firm-specific variable that I represent as set, okay? Then the exclusion restriction is that these set variables, okay, enter in the profit function, that the X tilde variables may be common to all the firms or may contain characteristics of different firms, of all the firms. But what we are considering is that they enter in the profit function of all the firms. For instance, if we are considering a model of competition, price competition, Bertrand competition with differentiated product, the characteristics that affect the product characteristics of every product will enter in the marginal profit of every product, okay? Because in the demand system, the market share that a firm has depends on his own characteristics, but also on the characteristics of the competing product. Then all these market characteristics affecting demand should be in X tilde. No exclusion restrictions there. No possibility of exclusion restrictions there, okay? But suppose that there are some characteristics that affect the marginal cost. For instance, the wage rate that a firm pays to his worker, or the wholesale prices that pays to the providers of the product, or some installed capacity of the firm that affects his marginal cost, or the capital stock of the firm, or if we have been able to estimate total factor productivity, the total factor productivity. We know that all these variables affect the marginal cost of a firm. But in principle, okay, it's very common assumption in our economic models that all these variables that affect the marginal cost of a firm, okay, do not affect They can be correlated, of course, with these same variables with other firms. But these variables do not have a direct effect on the marginal cost of competing firms. That is the exclusion restriction, okay? The wage rate of your competitor does not have a direct effect on your behavior. It has an effect on your behavior. How? Through your beliefs about the behavior of your competitor. They will enter here, okay? In your beliefs about the behavior of your competitor, but not in your marginal cost, okay? And because they are cost variables, not in your marginal, okay? And I'm implicitly also distinguishing here between variables affecting demand and variable affecting cost, okay? Okay, then once we have this, I think that it's quite straightforward to show that we have non-parametric identification, okay? Then give me 3 possible values, okay? You can get something more formal, but this is, I think that is more intuitive, okay? Give me 3 possible values of the wage rate of your competitor, okay? This excluded variable. Let me call it A, B, and C. And I obtain what is your behavior, represented by this quantile function. If the wage rate paid by your competitor is high, let me start providing some intuition, okay? The intuition basically is that suppose that we observe that the competitor has increased the wage rate that pays to his worker, okay? Keeping everything else equal. And then we observe that this firm, okay, the firm that has not experienced the increase in wages, but the competing firm, increases prices. According to this story, the reason why this firm has increased prices is because she believes that the competitor is going to increase prices, okay? Because it has a higher wage rate. Now, I believe that the price of my competitor will be, I do not observe the price of my competitor, there is incomplete information, but I expect that the price of my competitor will increase, okay? Or the probability that she charges the high price will increase. And that's why my probability of charging the high price will increase. Then the fact that we observe that with this change in the wage of a competitor increases the probability that this firm charges a high price reveals information about the beliefs, okay? If the beliefs had not changed, this firm had not changed prices at all, because the price of the competitor does not have any direct effect on the profit of this firm. The only way, according to this framework, that the wage of the competitor affects this firm is through the beliefs, okay? And that's what we are exploring, okay? If we look at the difference in the quantile in 2 different values for the wage of the competitor, basically we are taking the difference in this equation for 2 different values of the X variable that enters in the beliefs, but does not enter here, okay? Neither here, not here. Then basically we are getting rid of this additive term here, okay? By taking this difference, okay? We do the same for 2 other values, or for values C and A. And basically, we get rid of the constant term. Now we have now we don't have yet separation between beliefs and profit. We have the product of beliefs, of a function of beliefs and a function of profit, okay? But now we can get the ratio between these 2 guys, because these 2 terms do not depend on the wage of the competitor, okay? And therefore, okay, they are the same, okay, under the 2 different scenarios. And then we can get rid of them just basically by taking the ratio between these 2 equations. Would tell us that this ratio beliefs, this is an object that only depends on beliefs, is identified from the behavior of the firm under 3 different values of the wage of the competitor, okay? And we have identification of beliefs under this exclusion restriction. And this can be done for every value of X tilde and the wage of firm I, okay? Then this is in general identification everywhere, okay? Once we have this, of course, you can test unbiased beliefs, Bayesian mass equilibrium, rationalizability, as I have mentioned before, okay? I have not included it here, but this identification result applies also, you can verify by yourself. There is nothing, no role here at all, the fact that we observe the revenue function, because notice that we are removing the revenue function, okay, together with the marginal cost function, okay? Basically there's additional over-identification restrictions if we know the revenue function, but this identification result is exactly the same, basically, the one that I have presented, knowing the marginal revenue or not knowing the marginal, okay? Okay, the result, I have discussed it with only 2 players implicitly. It can be extended to the continuous choice case, to order multinomial choice models, and as we are going to see now, to dynamic games. And also, under some additional restrictions, I have assumed all the time that we know the distribution of F. With continuous decision variables, we can also identify the distribution of F, as is well known in the literature of auctions, okay? The distribution of F, not the beliefs, okay? Questions so far? Please.
Are there any limits to what you can identify from this belief function? I mean, there's a ratio, right? And stuff is canceling out.
Definitely. So far, this will be useful only if you want for testing, basically, different assumptions about beliefs, okay? Because we can always construct this object for whatever assumption about beliefs we for instance, if we want to test Bayesian mass equilibrium, we will construct this object using the actual choice probability of your competitor. And then we will have this ratio of difference, but using the choice probability of the competitor. That will be the test. If we want to use these now to estimate the payoff function, we need, as you can see, we need to impose restrictions. We need to assume, make some assumptions about the values of these beliefs at 3 points in the support of the wage of your competitor, okay? And then there are different ways in which we can do this, okay? You can say, okay, let's consider that those states, for instance, following the Arias presentation before, let's suppose that those states that have been visited very much in the past, they are states where these firms know very well how the competitors will behave. Then let's impose in this very frequent state, let's impose that we have rational expectation in the states, the 3 states that have been most frequent in the past of things like that. Or they are more frequent in different geographic markets if these firms are competing in different geographic markets, okay? You can consider that, well, perhaps you have elicited beliefs, but elicited beliefs in only some particular values. And then we can say, I'm going to use the elicited beliefs in this that I have from the data in these 3 data points. And then for the rest of the belief function, I will use this function, okay? But yes, you need 3 restrictions, 3 points in the support of this excluded restriction variable to identify, to fully identify the belief function. Yeah, that's important. Of course, a different issue is once you have estimated the model counterfactors, okay? The idea is not going with this belief function, non-parametric belief function to do counterfactors, nothing that you can do about it, but more like obtaining results about the identification of the payoff function that is robust to assumptions about beliefs, okay? Okay, then let's consider an extension of this static model, game of incomplete information, to a dynamic setting. Again, we have n firms indexed by I, every period t. They should make an investment decision. And let me now focus on the discrete choice version of the model. They have a discrete choice of capital J plus one possible alternative. And we have this one period profit function that depends on the action of the player, the common knowledge state variables, and this private information that this X should not be an X, should be an A. Depends on the action that the players. And then we have other primitive of the model, that is the transition probability of these common knowledge state variables. That depends on the action of all the players, okay? And it follows a control Markov process, okay? Epsilons, as before, are independent private values, not only independent across players, but also independent over time, okay? Everything that is serially correlated is in X, okay? For simplicity, okay? But important restriction, okay? In some assumptions that I'm going to maintain here. Of course, we are not going to impose Markov perfect equilibrium. That's what we want to relax, okay? But we are going to maintain some features of Markov perfect equilibrium, okay? Particular to reduce the dimensionality of the state space, okay? We are going to assume that players' strategy depend only on payoff relevant state variables, okay? And in our setting, that means that strategies are a function of X and the epsilon of the firm, okay? Second, that firms maximize intertemporal payoff, okay? And third, that firms are quite sophisticated here, okay? In the sense that they know how, under different scenarios, they will behave themselves in the future, okay? If you tell me what state I will be, and you tell me the belief that I will have in the future, I know how I will behave in the future given a state and beliefs, okay? They don't have biased beliefs about that. The only source of potential biases, okay, is that they do not know the strategies of the competitors, okay? And we are going to maintain that there is rational beliefs about their own behavior in the future, but they don't know, they might be biased in the behavior of their opponents today and in the future, okay? Then basically, all these are assumptions embedded in the Markov perfect equilibrium. The one that we are relaxing is the fourth assumption that imposes also that firms have equilibrium beliefs about the behavior of the competitor. That's what we are relaxing, okay? Okay, then this is, according to these assumptions, this is the strategy function of firm I at period t. And we can represent it probabilistically integrating over the distribution of epsilon, okay? And this is the CCP of player I at period t, okay? And now, because beliefs can be different to the actual choice probabilities of the competitors, as before, we need to introduce an object that is the beliefs of player I about the competitor. And now before, we had to introduce only the belief that a firm has about the behavior of your competitors today, because we are competing today and the future doesn't matter, okay? But now, to form the optimal behavior, or to form the expected value, the expected intertemporal value, a firm needs to form beliefs not only about the behavior of the competitors today, but also tomorrow and after tomorrow and so on. It needs the whole beliefs, okay, of the competitors at every period in the future, not only today. Then this is a huge object, okay? Basically, that's why I'm introducing two sub-indexes here. This means that beliefs are formed at period t, but they deal with the distribution of the behavior of the competitors at period t plus s periods ahead, okay? And let me represent it here in the different rows. We have when beliefs are formed. This is the beliefs of a player at period 1, at period 2, and at period 1, this firm needs to form beliefs about the competitors. At period 1, I don't know what is the prices that my competitors will choose today, but I need to form beliefs also at period 2, what will be the prices that they will choose at period 2 and at period 3 and so on up to the last period of the game, okay? And if there are infinite periods, forever in the future, okay? Okay, then we have all these functions affecting the behavior of a player at period 1. And the same at period 2, all these beliefs will affect the behavior of a player at period 2, okay? Notice that we are not imposing any restriction on the relationship between these beliefs, okay? Notice that this belief here and these beliefs here correspond to the same target. It's the behavior of my competitors at period 2, okay? Then, for instance, Bayesian learning will impose some restriction between what beliefs I had at period 1 and what beliefs I have about that target at period 2. We are not imposing any restriction, okay? Then this could be consistent with Bayesian learning or no, with any other form of learning, okay? Okay, then we have this huge dimensional object, okay? Then suppose that at every period t, a player has this vector of beliefs about the behavior of competitors now and in the future, okay? Then now we can construct for every period now or in the future, for every period t plus s, we can form the expected payoff of firm I integrated over the action, my beliefs about the action of my competitor, okay? Using these beliefs, okay? Then this is a well-defined object, okay? That is based on my beliefs and my primitive, that is my payoff. Similarly, I can construct, if I have these beliefs, I can construct the transition probability of the state variables, okay, of x, given that that will depend only on my current action and the current state, if I believe that the competitors will behave according to this probability distribution. And it is the integral over the distribution of my competitor's behavior of this primitive, this pi is a primitive, this f is a primitive, that is the primitive transition probability of the state variables, okay? And if I know payoffs, and if I know transition probabilities of state variables, we have a single agent dynamic programming problem. Now, given this object, firms will solve basically a single agent dynamic programming problem, okay? Then let me define, I have not introduced it here, but in the context of this single agent, I have not included the Bellman equation, anything, but believe me, let this small v be the conditional choice value function of this single agent, if you want, dynamic programming problem. Now, given these beliefs, I'm solving this dynamic programming problem, and this represents my intertemporal value. If I choose action A today, the state is X, and I believe that my competitors will behave according to this belief function, okay? Let's suppose that the epsilons, for simplicity, have a logit structure. Then this is my best. These are now the restrictions of the model, okay? The restrictions of the model say that this choice probability, this CCP that we can identify from the data, is equals to this function, okay? Again, we can invert this logit probability, okay? And that is, again, pure reveal preference. The observed behavior of a player reveals directly information about the conditional choice value function in the dynamic programming problem that this player is solving, okay? That's not the identification problem. The identification problem is how now, given that we know this conditional choice value function, we can separate between this primitive that is the profit function and the beliefs of the players, okay? That's the problem that we are trying to solve here. Okay, then let's look, how much time do I have?
15 minutes.
Okay, okay. Let's look at this because there's some difference with the identification result that we have seen in the static model, okay? And dynamics will matter here for the identification result, okay? And let's see this problem in some detail, okay? Then we can separate two components in the conditional choice value function, okay? because I don't know the actions of my competitors today, I need to integrate over the distribution, this B at period t, that represents the behavior of my competitors at period t. Okay, the vector. This is a vector with all the probabilities of all the possible actions that my competitors can take. And this is also a vector pi with my profit, given all the possible actions that my competitor, each row in this vector are the different the profit and the different possible actions of my competitor. Then the product of this vector and this vector represent just my expected profit today. Okay, but then I need to account for the continuation value. Okay, then this is my continuation value today, my expected value of future profits, given that I have chosen alternative A, and this is the state. And this continuation value depends on my beliefs, but not about my beliefs today. Depends only on my beliefs about the behavior of my competitors at period t+1 and after. Then these beliefs here are different. In principle, they can be different than these beliefs here. Okay, I may think that in the future my competitors may behave differently than today because there is learning, because there is non-stationarity, because multiple reasons. Okay, and these are different objects. Okay, and I'm using C to represent continuation values. Okay. Okay. Then we have data. Okay. We have the Hodge-Miller inversion, as I have mentioned, and we want to, let me consider now that this is data, okay, from Hodge-Miller inversion. We have obtained this as function of the choice probabilities, and we want to separately identify basically these B's and these Pi's, okay? Okay, then this is like, okay, this assumption is, I have not mentioned it before, but perhaps it's more relevant in dynamic games than in static games. We are going to observe these firms playing this game in multiple markets, okay? But we are going to pool observations from multiple markets to estimate choice probabilities, okay? Well, suppose that we have multiplicity of equilibria and firms are playing different strategies in different strategies because multiplicity of equilibria in different markets. Then we are not going to be able, by pooling markets from multiple equilibria or where firms are playing different type of strategies, we will never get basically the actual beliefs, okay? We are going to get a mix of beliefs. Then under the assumption of Markov perfect equilibria in empirical application, a standard assumption is that we have multiplicity of equilibria in the model, but not in the data, okay? This after conditioning on some observable variables, okay, and the pair of relevant observable variables, two markets with the same observable variables are playing the same equilibrium, okay? Which of course is not a trivial restriction, okay? Then here we are not talking about multiplicity of equilibria, but we are talking about beliefs. Then we are assuming that the similar assumption is to say a firm has the same beliefs in two markets that they have the same fundamental, okay? The same pair of relevant state variables, okay? They are not, as someone mentioned before, they are not sunspots, okay? Or if they are sunspots, they affect all the markets in the same way, okay? Okay, then this is an assumption basically and this is an assumption just to be able to pool. If we had very long time series for a single market, we will not need to make this assumption. But we are pooling multiple markets to obtain choice probabilities. That's why we need it. Okay. The second is the same type of static exclusion restriction as before. Here I unfortunately have changed the notation, but basically I'm saying the same thing as before, where we had said before, now we have S, okay? And what we have X tilde before, now we have W. Then W are the variables that are common that enter in the profit functions of all the firms, okay? In the example of price competition with product differentiation before, all the product characteristics that enter in the demand will be in W. All the variables that affect the cost of all the firms will be in W. What is in S? Variables that affect only, let's say, the marginal cost of firm I, or the marginal cost of firm 2, but the marginal cost of a firm, but not the other, okay? Okay, then this is the exclusion restriction. SJ does not enter in the profit function of firm I, okay? Now, this is not enough to have identification of beliefs in the dynamic case, okay? Because without further assumption, SJ does not enter in the current payoff, but it can enter in the future payoff if the information of firm I about SJ helps this firm to predict the evolution of the state variables. It will enter through the continuation value, okay? And therefore, it will be an exclusion restriction that will not be very useful because it does not enter it does not enter here, okay? But it will enter here because the probability distribution of the state variables at period t+1 depends on my information about the wage that my competitor pays to his work at that period t. It does not enter in my profit today, but it enters in my prediction of the evolution of this. Okay? Then to have the same type of exclusion restriction or the same implication of the exclusion restriction in a dynamic context, we need that SJ not only does not enter in the payoff function, but does not enter in the transition probabilities of the S variables. Okay? Then basically, we need this exclusion restriction. Okay? We need that the transition probability, the transition probability of the W's is completely unrestricted, but of this variable, we should have, you can interpret it as a finite dependence restriction. Okay? Once we condition on the action of a player, the S variable does not depend on the previous value of the S variable. Okay? Fortunately, we have many examples of this in IO. Okay? For instance, the most obvious is market entry. Okay? And a model of market entry. First, what is the exclusion restriction? Whether your competitor was an incumbent at previous period or not. Why this is an exclusion restriction that satisfies this condition? Because if my competitor is an incumbent or not at previous period, does not have any effect on my profit. Okay? What is important is whether my competitor is competing with me today or not. I'm not assuming it can be extended to time to build. But for the moment, let me consider I'm discussing here without time to build. Every period, the decision of entry is affected on the same period. Okay? Then what is important for my profit is whether my competitor is competing today with me or not, but not whether it was competing or it was an incumbent at previous period or not. Okay? And my competitor being an incumbent at previous period affects his entry cost, the same thing as whether I was an incumbent or not at previous periods affects my entry cost. But my entry cost does not depend on whether my competitor was an incumbent at previous period or not. Okay? Of course, knowing that whether my competitor was in the market at previous period or not is a very strong predictor of whether it will be a competitor today or not, because there are sunk costs, and in some industries there may be substantial sunk costs of entry. And if my competitor was active at previous period, I know that it's quite likely that it will continue being active this period. If it was not active at previous period, I know that it's quite unlikely that it will be active today. Okay? Okay, then that is going to affect my behavior, but my behavior through my beliefs about my profits today. But not only about my profits today. This condition also satisfies this dynamic exclusion restriction. Okay? Once I know whether my competitor is active today or not, whether it will be active next period or not, does not affect whether was he active at period t minus 1. Okay? Being active at period t minus 1 does not have any effect on my competitor's entry decision once we take into account whether it was active. It does not have any effect on the entry decision at period t plus 2, at t plus 1, sorry, once we condition on the entry decision at period t, okay? Once we condition on at, okay, at minus 1 does not have any effect on at plus 1, okay? And that's the exclusion restriction here, okay? Similarly, for many other capital decision models, suppose that we are thinking in a model of competition in quality, okay? Every period, firms has to, like in Pekes and Maguire type of application. Every period, firms need to choose the quality of their product, okay? Let's consider something different than Pekes and Maguire, and suppose that every period a firm can choose freely which is the quality of its product. Every period a firm, we are thinking, for instance, competition in hotels, they have to choose whether they have 1 star, 2 star, 3, 4, or 5, okay? And then a hotel with 3 stars may decide to upgrade to 5 stars, okay? They can upgrade in 2 scales in 1 period. Of course, this can be very unlikely because the adjustment cost can be very convex with the number of stars that we change. But in principle, you can change any number of stars, okay? That's different to the quality ladder type of model where you can only choose to increase 1 or not. In the quality ladder, we will not have this condition here. But in this model that I'm considering here, what in principle, every period a firm can choose any level of quality, but they are convex cost of adjustment, we have that the quality at period t plus 2, or t plus 1, sorry, depends on the quality of the firm at period t. But once we condition on the quality at period t, does not depend on the quality at period t minus 1, okay? And that's the condition that we are considering here, okay? I don't have any time, my friend.
Oh, no, you have 10 more minutes, yeah.
Okay, okay. Okay, then given these 2 conditions, okay? Now we need these 2 exclusion restrictions that, of course, they are restrictive, no doubt about it. But there are a good number of applications in dynamic games in I/O where these conditions hold, okay? Although where these conditions, where we are willing to assume these restrictions, okay? Then basically we have a similar problem as before, okay? We can basically choose 3 values of the excluded restriction of the S value of your competitor, and then we can construct basically these same statistics, okay? This statistic that depends only, or this object that depends only on beliefs is exactly equal to this object, but where we have the choice probability of player I, okay? Then the behavior of player I under this condition reveal information about this beliefs object, about this object that depends only on beliefs, okay? And again, then given this, we can test restrictions about equilibrium beliefs, and we can also test, notice that, of course, we cannot identify anything, notice that we have completely got rid with this assumption of this object, that is this super complex object that is the continuation value that depends on all the beliefs in the future, okay? This second assumption here, okay, is what allows us to get rid of all these continuation values. This kind of finite dependence type of assumption allow us to control for all these continuation values, okay? And then there is nothing basically in the behavior of player I that we are basically, that given our approach, identify anything about the beliefs about the future. All what we are identifying are beliefs about the present, okay? But now, once we have this, okay, and if we are willing to assume to restrict these beliefs to take a known value, okay, to be, for instance, rational beliefs at 3 points in the support of this exclusion restriction, then we will be able to recover these contemporaneous beliefs, not future beliefs, but we will be able to recover contemporaneous beliefs, and we will be able to identify the payoff function. Then we will have both payoff function and contemporaneous beliefs identification. Okay, please.
This one asks when the identifying variation is from markets, whereas it has to be markets. It's not. This is like an individual time with market variation.
Because I'm including T as a sub-index, basically everything is at period T, then basically what we are saying is these firms, that's a very good question, these firms are competing in all these markets. Then there is a market where I observe that my competitor has at previous period quality 1, other market quality 2, another market quality 3, okay? And that, okay, according to this assumption, the previous period quality of my competitor should affect my behavior. Then we are using this multiple market, basically everything the same, all this market, everything the same, all the exogenous state variables and the other endogenous state variables exactly the same. But we observed that in these 3 markets, the quality of my competitor was different, okay? And that's basically how we are constructing these choice probabilities or this log of ratio at 3 different markets, or we observe 3 different values of this variable, okay? And we have this geographic market is important, okay? Otherwise, let me say that if we are assuming a stationarity, we could do the same at different periods. Here, implicitly, I'm not assuming a stationarity, but please.
Yes,
Okay, perfect, okay. Okay, then this is basically what I was saying. This log of ratio at 3 different markets, okay, or 3 different values for my competitors, give me exactly, reveals the belief that this player has, or this object of beliefs, okay? And if we are, and this by itself can be used to test any hypothesis basically about beliefs. But of course, we may want to have beliefs everywhere, because if we have beliefs everywhere, then we will have identification of payoffs everywhere, okay? And then that may come from restrictions about beliefs, for instance, rational beliefs at 3 different points in the support of the state variables of my competitor, okay? In this paper with Arvin Magazine, we applied this idea. This is a very super simple empirical application, just to illustrate this approach. These are not exactly the early years of the fast food hamburger market in UK, but they were soon after the introduction of this product in the UK. And then we consider the competition between McDonald's and Burger King in the United Kingdom. We have more than 400 local market districts in the UK between years 1990 and 1990. Okay? And the idea is that because this was a relatively new industry where you are going to see that these 2 retail chains were expanding very importantly during these 5 years in terms of the number of stores, they may have biased beliefs about the entry decision of the competitors, okay? And you see, this is Burger King, McDonald's, the number of markets of this district where they have stores. You can see that it was increasing substantially during this period. The increase in the number of markets, the number of new markets where they entered. We do not observe exit of a store during this period. Of course, there has been a lot after that, but during this period, there were not exit. This is the total number of stores in all the markets. This is the increase in the number of stores over all the markets, and this is the evolution of the number of stores per market. Okay. Okay, you can see that that McDonald's were always basically the leader, though there was some catch up by Burger King in terms of the difference between the average number of stores and the average number of markets. Then we consider a dynamic game of competition in the number of stores. Basically, the strategic variable of this firm is whether to be present in the market, but not only to be present, but how many stores do you have in the market. That is the key decision that we are considering here. Then K represents the number of stores that a firm has in this market. This is the state, this is the number of stores at previous period. And A is the decision of whether to increase the number of stores or not. And during this sample period, we observed that in a given market, in a given district, there were not more than one store opening. Okay, there were not two. Then with a binary choice, we can model this game. A plus K, of course, represents the total number of stores available at period T, that is the ones existing in last period, and the new ones, the new one, if any. S is the key exclusion restriction that we are going to use in this model. This represents the distance. It tries to capture economies of density. It represents the distance of market M, and it's endogenous. It's dynamically endogenous, not endogenous in the model, but it's dynamically endogenous in the sense that it's going to evolve endogenously. Okay, it's not the distance of market M to the headquarters of the firm. It's the distance of market M to the network of stores of this retail chain, and in particular to the network of a store. Like, what is the distance between this market M and the closest market where this firm has a store? Okay, and we are trying to consider, well, and this is empirically is very relevant. It's a variable that has a lot of predictive power in the entry decisions. And the economic interpretation, or at least our economic interpretation, is that the cost of operating new stores, because logistics, because the distribution cost, can increase with the distance to your network. This is the same idea as in Tom Hall's paper about the expansion of Walmart. Okay, and this is a variable that tries to capture economics of density. Okay,
but implicitly you sort of assume then that the decision to enter, say, market M is done independently of.
That's right. That's right. Then there
you seem to indicate that there's sort of like a.
Yeah, you are completely right. You are completely right. Yeah, I cannot. Yeah, you are completely right. And given that this is a very significant, it has a lot of predictive power, one will consider that this is a network decision problem. Okay, as in homes. Okay, we are not modeling that, but you are 100% correct. Yeah. At the same time, I think that it makes the paper inconsistent somehow, but I think that it does not have any effect on basically the validity of our exclusion restriction. Okay. Okay, then the profit function is equals to the variable profits minus the entry cost minus the fixed cost. And we model this, we have only choice data, and we don't have revenue or cost information. Then basically we consider the following model for these three components. The variable profit is like an index of market characteristics that give us the dollar amount, if you want, or some index of the profitability of the market. It includes population density, income, and other variables. This is the number of stores that a firm has in the market, okay? And this term here is the profit per store, okay? And then the profit per store depends on how many stores you have in the market and how many stores your competitor has in the market. Then this first term will be a cannibalization effect. If you increase the number of stores, you may be increasing your variable profit, your total variable profit, but this increase is going to be less than linear, okay? It's not going to increase proportionally because there will be cannibalization. And we expect this parameter to be negative, and we estimate it negative. And this is the competition effect. Your profit per store should decline with the number of stores of your competitor, okay? This is the entry cost. This is the cost of opening, of increasing, or opening a new store, okay? And it has a fixed component, but it also depends on whether it is your first store or you already have a store. There may be some economies of density if you want within a market in terms of opening a second store can be cheaper than opening your first store. And this is where we incorporate basically these economics of density across markets, okay? The closer is this market to your existing network, the smaller is the cost of opening a new store, okay? And this is also where we introduce the private information in the entry cost. And there is a fixed cost that is paid by a firm, every firm that is active in the market every period, either a new firm that has yet entered or it has entered several periods ago. And it depends, it's positive only if you have any store. And it has a linear, it's basically a function of how many stores do we have, okay? And this fixed cost, depending on, it has a linear component on the number of stores, and it has a quadratic component. Then if the quadratic component is positive, there will be these economies of scale with the number of stores. If it's negative, there will be economies of scope in the number of stores in the fixed. Okay? Yep, please. Please.
Why doesn't this the SINT, didn't that matter more when it's your very first store? And another store in that new market?
Here we are not interacting this indicator with S. Then here we are assuming that's a very good. I'm sure that we eventually tried an interaction between these two terms, but probably it was difficult to separately identify. And then we assume that these economies of density matter the same if it's the first store or is the second or the third.
If you don't have a store, it's going to be another zero.
If you don't have a store, notice that this is multiplied. If you open a store,
The market, then this probably will go to zero, no? Because you already have a store there. The distance from the center is zero.
Oh, you are completely right. Yeah, exactly. Yeah. Automatically, this will become This will become zero and will not have any effect. Great. Okay. It's clear that Aureo was the editor, and all the good ideas in this paper came from his comments. Okay. Then this is based on the identification result that I have described before. This is the test for unbiased or equilibrium beliefs, if you want, of Burger King and McDonald's. Okay. Then we cannot reject biased beliefs for McDonald's, but we can clearly reject unbiased beliefs for Burger King. And it's interesting, in the paper you have more explanation to see where is the source of the bias, in which type of states, in which type of markets we find that the Burger King beliefs about the entry decision of McDonald's was biased. This is in markets that are relatively far away, that they are farther away from the network of Burger King, and is in the probabilities, is not in the probability that McDonald's enter the market. It's in the probability that McDonald's is going to open a second store given that Burger King enters. Burger King, there is clear evidence from the data that according to this estimate, that Burger King underestimated McDonald's reaction, if Burger King enters, McDonald's reaction of opening a second store, okay? And this is this market where McDonald's was an incumbent in a market that was far away from Burger King network, that Burger King underestimated the probability that McDonald's, after the entry of Burger King, will open a second store, okay? And therefore clearly overestimated its profit and tended to enter too much, okay, in this market, okay? Please.
Did that change over time?
Yes, exactly, because exactly the mechanism that let me say, okay, let me go to the interesting stuff, okay? Then we find that this matters for the estimation of competition effect very much and a little bit on the entry cost. But then the question that you are addressing is, what is the cause of these biased beliefs for Burger King? And depends on which year we are, okay? Because Burger King is expanding, and therefore eventually the network is going to cover all the markets, and because it's Burger King in all the markets, is not going to have biased beliefs, okay? Then because this expansion of the network, eventually this biased beliefs is very costly, accounts for 2.78% of the monopoly. This should be always normalized relative to the monopoly profits, for instance, because we do not observe profit themselves, only dollar values of profit. But this is 2.78% of the monopoly profits of Burger King in 1991. But by 1994, by the end of our sample, this was much, much smaller, okay? Definitely. Yeah, we see exactly that by this time, basically, of course, it's driven by our model, but by this time, keeping constant basically the primitives of the model, the probability of entry in this type of markets of Burger King was much smaller. There are many other explanations. Of course, it could be this, the remaining marginal markets are probably much worse than the markets that they entered before, and there may be other competing stories, but yeah, that's what we find. Okay, that's it.